Okay. Good evening. Good evening to everyone. So, in this lecture, we will discuss planar graph. Okay. A graph is said to be embeddable in a plane or planar if it can be drawn in a plane so that its edges intersect only at their endpoints. So, okay, a planar embedding of a planar graph is referred as plane graph. Here, a planar graph and a planar embedding of it is shown in the figure. So, this is a planar graph, and this graph is redrawn like this. This is, both of them are same graph, but here, if you look at the edges, these two edges are what intersecting. Okay, okay. But if you redraw this graph, for example, you keep this for okay. For example, this is C4. Okay, keep this one as it is, and then we'll keep this edge. Okay, instead of drawing like this, they are drawing. Okay. Uh, and I think yes. Okay, so they will put this vertex is here. Okay, they'll put this vertex is here. So instead of this edge, they will draw like this. Okay, they'll draw like this, and then from okay, and then this from here to one more edge, and here to this edge. Okay, so here, and from here to here they are redrawn like this. Okay, so now if you see this graph, this is same as this graph, but only the difference is what? So it the edges okay, its edges intersect only only at their ends. Okay, so now there is no intersection of edges. Okay, so like this here they are intersecting here, but if you redraw like this, they intersect only at the yeah, the endpoints of the vertices. So if it is possible to redraw the graph like this, then we call that graph is called a planar graph. Okay, we will saw some more examples. Okay, look at first proper definition. A graph is called planar if it can be drawn on a plane without intersecting edges. So here you can see here this is K4. Okay, so K4 is a planar graph. So look at this diagram. This is K4. Okay, this is the original graph. So the edges are intersecting here. This is not in the text, okay, but if you redraw this graph like this, okay, you can put like this. Similarly, these two edges, okay, is connected by like this. Instead of this edge, I am connecting like this. So and hence now the edges are intersect only at the endpoints. So and hence K4 is what? A planar graph. So another representation of you can draw like this also, the same graph, four vertices. Okay, so this is also K4. Okay, because each of the degree is what? 3, 3, 3, 3 degrees what? 3. So this is also another representation of K4. So here also the edges intersect only at the endpoints. Okay. So a graph is called planar if it can be drawn on a plane without intersecting edges. So planar graph K4 and a two plane embedding of K4. Already I I drawn how to draw K4 without intersecting edges. This is one of the way. This is another way. Okay. Actually, here there is some in this uh, again the same thing they are doing, but there is a small mistake I think here. Okay, look at this one. So here, uh, this is the original graph. 1, 2, 3, 4. Okay, 5. So I'll join like this. Okay, now there is no intersection. Okay, I don't have any problem. Now and then, yes, if I draw like this, it will intersect. But so I'll draw like this. Okay, similarly, if I'm going to join these 2 points here like this. Okay, and this edge. Okay. I think I drawn. You can count the number of edges. 1, 2, 3, 4, 5, 6, 7. Here you can check it. 1, 2, 3, 4, 5, 6, 7 edges. Okay, I think everything is correct. So you can redraw this graph like this. And hence this is planar. Okay, this is planar. I think they done some mistakes here. Okay, so I think this is wrong. Okay. So next, actually here it is mentioned the complete graph K4 n greater than or equal to 5. Already we saw an example. K4 is what? Planar. Okay, but the complete graph Kn from n greater than or equal to 5 is non-planar. That means what? K5, K6, K7, okay, and so on. So okay, is what? Non-planar. Similarly, Kn comma m, n and m are greater than or equal to what? 3 is also what? Non-planar. So that means they are K23 is planar. We will check it. K23 because here they are telling what m and n are what greater than or equal to 3. So K23 means here 2, here 3, or here 2, here 3. Okay. So K23 means complete bipartite graph. I will join like this. Okay, still I need to join what? 3 more edges. 1, 2, and then 3. So this is actually what? K23. So here the edges intersect only at the endpoints, and then K23 is also what? A planar graph. These points are not that much important. Okay, now I'll move to the problem or theorem. Prove that K5 is non-planar. Okay, so here just I will explain in the diagram. Actually, this is K5. Okay, complete graph on 5 vertices. So first construct the pentagon. So pentagon means U, V, W, X, Y, U. So this is pentagon. Okay, so first step. Okay, U, V, W, X, Y, U. Okay, this is the first step. Next, join U with W and X. Next, you should draw this diagram. Okay, but you should write what you are going to do. Join U with what? W and X by 2 edges U, W, and what? UX in the internal part. Okay, in the internal part of the pentagon. Okay. So if you draw like this, it will not cross the previously drawn edges. Okay, you can easily see that these two edges not cross the previously drawn the edges. Okay, next step. I'll keep this slide. I'll take a snapshot. Maybe I will put it here. Okay. Okay. So up to this we done it. So next step, join V with okay, X and Y by the edges. Okay, maybe maybe I will put a diagram here. Then you can easily understand. Again, I need to step 3. Maybe you can write U V W X Y. These edges are already there. Okay, these edges. Now, what we are going to join V means this vertex V with what? X and Y by Vx like this, and then what? Vy in the exterior part of the pentagon. So Vx and Vy. Vx and Vy. Okay. Okay. So next, okay. So now still the newly drawn edges is not intersect any of the previously drawn edges. I think you can see clearly. Okay. Next, the vertices. Okay, now check it. How many degrees for each vertex? Degrees what? 4. Just for because in K5 all the vertices are what? Degree what? 4. So there is no need to write this, just for understanding. I'll write 4. This is 4 degree. V is also what? Degree 4. X is also what? Degree what? 4. Uh, W is degree 3 and Y is degree 3. So I need to join W and Y. Suppose if I draw like this, it will cross, it will cut this edge. Suppose if I draw like this, connect, it will cut this edge. Suppose if I want to go like this, okay, it will cross this edge. So anyway, okay, if you draw between W and Y, it will cross at least one edges which is drawn already in the graph. So that's why they're telling the vertices W and Y are in different regions, and the edges WY cannot be drawn without intersecting the previously drawn edges. So therefore, K5 is what? Non-planar. Okay. Next. So next theorem. Prove that a problem. Prove that K33 is non-planar. So K33 means here 3 vertices, here 3 vertices. So I'll call this is XYZ. This is what? PQR. So this is K33. Okay. Now let us assume that the vertex set V1 contains what? XYZ, and vertex set V2, because bipartite graph contains 2 partition. So V2 is what? PQR. Now first I'll put a dot like this, dot 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 dot. First I will join X with what? P, Q, R. Now I don't have any problem. Next, join Y with Y and Z with R. Okay. Okay, you can see in the next diagram. Okay, join uh, join Y and Z with R. That means YR and what? ZR. Join Y and Z with R through the edges what? YR and what? ZR without intersecting the previously drawn edges. So maybe I think you understand this one easily. That's why I don't draw the diagram. Maybe you can see here already. Okay, sorry. Okay, maybe I'll draw it. So P Q, sorry, X Y Z, X Y Z, and this is what? P Q R, P Q R. So first step we draw XP and then what? XQ and then XR. This is first step. The second step, I am going to join with what? Y and Z with the R through the edges YR and ZR. So in the diagram we can see. For each step, we should draw the new diagram. Okay, that is better. Okay, then only it is very clear. Okay, so yes, I drawn here. Okay, next step Y with what? R. Maybe I'll choose some other color. Y with R. Okay, and Z with what? R. Okay. So then there is no intersection. Okay, now okay, between the previously drawn edges. Okay. So this is Y. Okay, Y, and this is Z. Okay. Next step. Uh, okay. Okay. I think up to this we draw. Next Y with P and Q through the edges YP, maybe YP here, and then what? Uh, sorry, Y with the P. Y with P means Y to P here and Y to Q in this way. Okay, you can see here. Y to what? P like this, and then what? Y to Q. Okay, so next, maybe I'll choose some other color. Y to P like this, and then what? Y to Q. Okay, Y to Q. Okay. Now check the degrees. Okay. So each of the vertices should have what degree? What three. Here three. Here three. Here what? Three. Okay. Here two. Okay. Still you can draw something. Okay. Now I joined what? Y and P and what? Y and Q. Okay. So join Y with what? P and Q through the edges YP and what? YQ without intersecting the previously drawn edges. Next, join the Z and Q. Z and Q through the edge ZQ without intersecting the previously drawn edges. So I'm going to join Z and Q. Z and Q. Z and Q, like this. Okay. Wow. So okay. Now what is the degree of Q? 3. Degree of Q is what? 3. Only the degree of P and the degree of Z are what? 2. If I draw, if we connect these two, it will cross like this. If I go like this, like this, like this, if I go like this, again it will cross somewhere else this edge. If I go like this also, it will cross this edge. So P and Z are in different region. You can see here. Z and P are in different region. Edge ZP or PZ cannot be drawn without intersecting the previously drawn edges. So and hence what? K33 is non-planar. Okay. So just now we proved K5 is non-planar. K33 is also what? Non-planar. So some of the observation. So Kuratowski graphs. Okay. Uh, here, here you can see both K5 and K33 are regular graph. Okay, what is the degree of each vertex here? 4. Here the degree of each vertex is what? 3. So that's why they are regular graph. And both of them are non-planar, just now we proved. And the removal of one vertex or one edge makes the graph planar. From this, if you remove one vertex or any one edge from either this graph or this graph, the resulting graph is what? Planar. Okay, already it is non-planar. If you want to make it planar, you should remove what? Either you should remove one vertex or what? One edge. Okay. Kuratowski's first graph, this is called the Kuratowski's first graph, is non-planar graph with the smallest number of vertices. Why smallest number of vertices? The number of vertices is what? 5 here. This is also non-planar, but the number of vertices is what? 6. So that's why this is called non-planar graph with the smallest number of vertices. Similarly, this is called Kuratowski's second graph. Okay, this is also non-planar with the smallest number of edges, because the number of edges here 9, because 3 into 3 9, but here 10. Complete graph number of edges is what? N into n minus 1 by 2. Here n is number of vertices, so 5. 5 into n minus 1 is what? 4. 5 into 4, 20 by 2, 10. Here the number of edges is 10. Here the number of edges is what? 9. So that's why this graph is a non-planar graph with the smallest number of edges. Okay. The first and the second graph of Kuratowski are represented as K5 and K33. The letter capital K is for the to represent the Polish mathematician Kuratowski. Okay. Next concept, region. Okay. Before this, one more result. A graph is planar if and only if it has no subgraph homeomorphic to K5 or K33. So here, just to don't confuse with the word homeomorphic, because this word may be new to you. So it is better to remember like this. Okay. Suppose if I want to show that a graph is planar, okay, it should not have K5 or K33 as a subgraph. That's all. Okay, suppose a graph, okay, contains K5 and or K33 as a subgraph. That graph is not planar. Okay. This is a simple way to remember this result. Okay, next region. Okay, here a plane representation of a graph divides the plane into regions. Regions are called windows, or it is called face or mesh. So all of them are same meaning. Same meaning. Region, window, face, mesh. But usually we don't use window and mesh. Okay, usually we use either region or what face. Okay. So a region is characterized by, okay, this is the definition of region. A region is characterized by a set of edges forming its boundary. Okay, so for example, the region 1, okay, is bounded by this edge and this edge. Region 2 is bounded by this edge and this edge and this edge. So here, uh, these are totally how many regions? 6 regions are here. Okay, the fourth region is the infinite region. Okay, the fourth one is infinite region. Remaining all are uh, bounded region. Okay, so you can say it is an infinite region, or you can say uh, exterior face. Okay, exterior face. Okay, so here, this is here how many faces or regions? Totally F7. F1 to F6 are all bounded. F7 is infinite region or exterior face. So that means here F1, F2, F3, F4, F6 are interior face. Okay. Okay. Now here they are telling that the totally how many faces here? 1, 2, 7, and F4 is they are telling unbounded. It is called what? Infinite face. Infinite face or exterior face. And here also F4 is what? Infinite face or exterior face. So totally in this graph we have four faces. Okay. So next to Euler's formula, this is somewhat important for exam point of view. So here you can see in this graph how many phases. This is one, and two, three, four, and infinite phase one. That's why phase is what? 5. Number of vertices you can easily count. You can count it 10. Number of edges is 13. The Euler formula is n minus, that is number of vertices minus number of edges plus number of faces equal to 2. So you can check it whether it satisfies. Uh, this is for what? Connected planar graph. Okay, what? So connected planar graph, n minus e plus f equal to 2. Okay, this is a connected planar graph. I'm going to check whether the Euler formula is true or not. So n minus e plus f, n is what? 10, e is 13, f is 5. So 15 minus 13 is 2. So we verified Euler's formula is true for this connected planar graph. Planar graph or plane graph. Okay, now we will discuss this Euler formula now, and then remaining thing we'll discuss in the next lecture videos. Okay, now we're going to. Sometimes usually they will ask the question like this: state and prove Euler's formula for planar graph. That's it. So you should remember the statement. Okay, if G is a connected plane graph or planar graph having V comma E and F. V means what? Number of vertices. E means total number of edges. F means the total number of faces. As the set of vertices, edges, and the faces. Faces are what? Regions, respectively. Then the number of cardinality of V is number of edges, number of vertices minus number of edges plus number of faces is equal to 2. So the proof is by induction on the number of edges of G. So you know induction, mathematical induction. Here um, you are going to use mathematical induction on the number of edges of the graph G. Okay, first I'll start from, suppose the number of edges is what? 0. There is no edge. There is no edge means, okay, since G is a connected graph, okay, connected, so it is there is no edge means it should be what? K1. So it is what? K1. K1 means just dot. K1 means just a dot. So here n equal to what? 1. Number of vertices is 1. Number of edges, there is no edge, 0. So number of faces is what? 1. So that is a unbounded face or infinite face, or you can say exterior face, only one face. This is a face. Okay. Next, I'm going to check. N is 1, E is 0, F is 1. Okay. Yes. Sorry. So it is K1, so that the number of vertices is what? 1. Number of faces is what? 1. The infinite, that is the infinite region or infinite face. And the number of edges is 0. We know that. So I am writing the left hand side, cardinality of V minus cardinality of E plus cardinality of F equal to, this is 1. We know the edges is 0 plus 1 equal to, I am getting 2. So we proved the Euler's formula for a number of edges is what? Equal to 0. Next, suppose next the number of edges is equal to 1. So actually, usually we will do it for example, n equal to, suppose if I done it for n equal to 1 means I will not do it for n equal to 2. Usually I will not do it. Suppose here the number of edges is equal to 0 means directly you can assume, you can go for this step. Assume the result is true for connected plane graph. You can go to this step. But for more clarity, I am going to do one more part. One more part means, suppose cardinality of E equal to 1. So in this case also I am going to check whether the Euler's theorem is true or not. It is better to write, from my point of view, it is better to write in the examination. So cardinality of E equal to 1. Okay. So though it is not necessary means, actually this case is not necessary, but it is better to write. Okay. So then the number of vertices of G. Okay, what is the number of vertices of G is either 1. In this case it is 1. In this case it is 2. Okay, so suppose it is a loop means number of vertices is what? 1. Suppose if two the edges is what? Edges is 1. Here also edges is 1. Vertex is 1. In this case, here edges is 1. Okay, this is K2. 2 vertices K2. Okay, so you call this the second graph is what? K2. Okay. So first I will consider figure 1. So in figure 1, number of vertices is what? 1. Number of edges is what? 1. Number of faces is what? 2, because interior face 1, exterior face. So total face is 2. So left hand side of Euler's formula, cardinality of V minus cardinality of E plus cardinality of F equal to 1. This is also 1, so minus 1 plus 2. So you get 2. Okay. So we verified for the first diagram. Next, figure 2. In figure 2, number of vertices is what? 2. Number of edges is what? 1. Number of faces is also what? 1, because that is the infinite face. So on left hand side of Euler's theorem, okay, you should write cardinality of V minus cardinality of E plus cardinality of F. Cardinality of V is what? 2. Number of edges is what? 1. Number of faces is 1. So 1 gets cancelled, you get 2. So hence the result is true for what? The number of edges equal to 1 also, it is true. Next, assume the result is true for all connected plane graphs or planar graphs with cardinality of E minus 1 edges. Okay. So usually in a mathematical induction, we prove n equal to 1, and we assume the result is true for what? N minus 1, and we are going to prove the result for n. So similarly here, assume the result is true for all connected planar graph with the cardinality of E minus 1 edges. Okay. Next, if G is a tree. Okay, well, if G is a tree, there are here I am going to discuss two cases. If G is a tree, if G is not a tree. Okay, so G contains the number of edges is what? tree. Number of edges in a tree is what? Number of vertices minus 1. And the number of faces in a tree is only 1, because it does not contain, tree does not contain any cycle. So that's why if the number of faces is equal to what? 1 in a tree. So uh, hence the left hand side of Euler's theorem, number of vertices minus number of edges plus number of faces equal to. So I don't know the number of vertices in a tree, that's why I'll keep as it is. But I know the number of edges in a tree is what? Number of vertices minus 1. Okay. Number of faces is what? 1. So number of cardinality of V minus cardinality of V gets cancelled. So here we'll get finally what? Plus 1 plus 1, 2. So we verified, okay, in the case if G is a tree. Okay. Now, if G is not a tree, if G is not a tree means it contains a cycle. Okay. So I'll choose an edge in the cycle. Let X be an edge contained in some cycle of G. Okay. Now, okay, I'll draw a diagram. Suppose this is a cycle. So look at here. This is phase 1. Okay, this is phase 1. This is phase 2, and then this is phase 3. Okay. So if I remove one edge, that means if I remove this edge means, okay. So this phase and this phase are together. Now, after removing one edge, okay, the number of phases is reduced by 1, because if I remove this edge means the resulting graph is what? The resulting graph is like this. Okay, the resulting graph is like this only. So now total number of phases is what? 1, and the remaining is infinite phase. So if I remove one edge from the cycle, okay, so the number of phases also what? Reduced by 1. So using this observation, okay, I'll start again. G is not a tree. Then there is some cycle. I'll choose as edge X. Okay, this is the edge X. Okay, this is the edge X. X be an edge contained in some cycle of G. Then G dash. G dash is equal to G minus X. So this is G. This is G dash. G dash is equal to what? G minus X. Okay. So is a connected plane graph again. Okay. Here the number of edges in the original graph is what? The original graph is in general. I am speaking in general. In general, the number of edges in the graph G is what? Cardinality of E. Okay. The number of edges in this graph. What is this graph? G minus E. I am removing this edge. So the number of edges for this graph is what? Number of edges minus 1. Okay. So, but what you assume that the result is true for all connected plane graphs with what? The number of edges is what? Cardinality of E minus 1. So our result is true for our result means what? Euler's formula is true for the graph G minus E. Okay. So okay, yes. So G dash is equal to G minus X is a connected plane graph. G dash contains how many edges? Okay, a cardinality of E. Okay, a cardinality of E minus 1 edges. So for the graph G dash, Euler's theorem is true. So one more observation: the number of vertices in G dash is same as what? The number of vertices in G dash. Sorry, not G dash. This is G dash. G dash is equal to what? G minus E. The number of vertices in G dash is same as the number of vertices in what? G. There is no change in the number of vertices. So I will take the number of vertices in G is equal to what? cardinality of V. So all of them are same. Number of vertices in G dash is equal to number of vertices in G is equal to, I will take it is equal to what? Just the cardinality of V. But the number of edges in G dash is what? Number of edges in G minus 1. You can see here. I removed this edge. That's why in G dash, one edge is reduced. Okay, so the number of edges in G dash is equal to number of edges in G minus 1. I will take this is equal to just cardinality of E. Okay, I don't write E of G. Instead of E of G, I'll just write what? Just E. Okay. Now I already told you number of faces in G. Okay, okay. Suppose number of faces in G is what? Here it is 3 means here it is what? 2. Suppose if it is K means here it is what? K minus 1. So one phases is what? Reduced. So that's why. Okay. So the number of phases in original graph G is cardinality of f of G. So number of phases in number of phases, okay, in G dash is equal to number of phases in G minus 1. Okay, I will take instead of f of G, I'll just write what? F. So by induction hypothesis, I already told to you, okay, G dash has how many edges? G dash has cardinality of E minus 1 edges, and hence Euler's theorem is true for what? G dash. So that's why Euler's theorem is true for what? G dash. By induction hypothesis, this is true because of you assumed here what? Assume the result is true for what? Connected plane graph with cardinality of E minus 1 edges. G dash also has how many edges? How many edges G dash? Cardinality of E minus 1 edges. So that's why by induction hypothesis, Euler's formula is true for G dash. So what is Euler's formula? Cardinality of V of G dash minus cardinality of E of G dash plus cardinality of F of G dash is equal to 2. But we know that cardinality of V of G dash is equal to what? Cardinality of V. And we know that cardinality of E of G dash. What is cardinality of E of G dash? Cardinality of cardinality of E minus 1. Cardinality of E minus 1. What is the number of edges in G dash? Number of edges in G dash is equal to number of F in G. That is what? Just cardinality of F minus 1. Equal to what? 2. This 2 is I'll write as it is. Now cardinality of E minus what? Cardinality of E, and then plus 1 minus 1 gets cancelled, plus cardinality of F equal to 2. So, and hence we proved the theorem is true for what? For G. Why the theorem is true for G? Because for G, the number of vertices usually we call it is what? For number of vertices, V of G. V of G is what? Same. Similarly, for G, what is the number of edges? Number of edges we are taking. Just what? Cardinality of E. You can see the statement. Okay. So for G, just we are taking what? Cardinality of V, cardinality of E, cardinality of F. Okay. So that's why this is equal to 2, and we proved the Euler's formula for G. Okay, we proved Euler's formula for G, and hence the completes the mathematical induction and completes the proof of the theorem. That's all. I'll stop here. The remaining thing we will discuss in the next class. Okay, thank you.